Okay, so we're going to go ahead and talk about perfect rolling motion where an object essentially rolls without slipping. So I want you to think about on a really icy day, car wheels will kind of like skid around and they will not roll like in perfect rolling motion where something just rolls without slipping or skidding. So you'll see this problem come up all the time in AP problems. Rolls without slipping, that's just perfect rolling motion essentially. So let's go ahead and look at it. So if we were to break apart rolling motion, so if we imagine like a bike tire rolling to the side, it is moving side to side, so it's going to have translational, if I can spell that, and it is also going to have rotational because it is rolling. And these are essentially the two parts of it. So I'm going to go ahead and draw at certain points. Actually, I want you to do it first. Go ahead and guess what the velocity vectors are at each of the points I drew for translational motion and do the same thing for rotational. Okay, so now that you've done it, I'll go ahead and do it. So translational, something is just, again, these are the velocity vectors, just moving, and we should assume, I should have said it's moving to the right, and it is rotating clockwise. Sorry, should have said that. So if it's rotating clockwise, it's going to rotate like that, rotating around that. And again, rotational, we're just imagining everything's rotating around that center point, and it's rotating clockwise. Cool. So now let's go ahead. We know that the perfect rolling motion is going to be the sum of the translational and rotational parts. So let's go ahead and draw, I'll call it the total. Let's go ahead and draw the total. Okay, so let's look at the top one. So we have velocity, I should label these as velocity. We have one velocity and two velocity vectors. They're just going to be a longer velocity vector that way. So we have one to the right, one down. That's going to just be at an angle for this one. Okay, this one we have one going left, one going right. Those are just going to cancel out. So that velocity is going to be 0 at the bottom, which we're going to get to that in just a second. And again, all of these are on, like, let's say it's on a surface. Last one, we have one going up, one going to the right. It's going to average out that way. The middle, it'll just be going to the right. Cool. So at the bottom, the wheel is at rest for a split second. Very interesting. So if it is at rest for a split second, this means friction can do no work. So this means friction does no work because work is equal to change in KE. If there is no change in KE, this is with 0. Work is 0. So this means force of friction does no work. And I want you to keep in mind, for something to roll, it needs friction to roll. And it will need static friction. So force of static friction is needed for rolling. If it's a really icy day, it is going to be impossible to get those car tires moving and rotating. So we need friction, static friction, to keep something rolling. Wow, that's fascinating. So this means friction does no work. No energy is going to be lost to friction if we have perfect rolling motion. Wow, pretty cool. Let's go ahead and solve the problem involving these ideas now. Okay, so let's go ahead and look at this problem together. So we had a solid ball. Okay, let's go ahead and draw it. Of mass m and radius r, starts from rest and rolls down a hill without slipping. Okay, that's going to be key right here. Rolls down a hill without slipping. That means we are dealing with perfect rolling motion. If its center of mass starts the total distance of h, so this is going to be h. Find the ball speed at the bottom of the hill in terms of the given radius. Okay, so we are going to want to find, so again, this is radius r. We are going to want to find this speed all the way down here. Cool. So let's go ahead and look at it. So again, anytime we want to find speed, let's think about what type of strategies and things are changing height. Conservation of energy is going to be our friend. So I want you to label what type of energy it has at the top of the hill and what type at the bottom. Okay, so at the top, it's not moving, so no kinetic energy. We do have gravitational potential energy because it's some height above the ground, and I should say the bottom where it ends up is height is 0. At the bottom, okay, so it's definitely moving linearly because it had to go down this. So it's going to have some sort of KE translational, but now it's rolling without slipping. So we're also going to have some rotational kinetic energy because it's rotating as well. So we used to have just UG equals KE translational, but now we have some more in the mix. go ahead and get the setup and start plugging things in and then check back into the video. Okay, so we have UG at the top equals KE translational plus KE rotational. Let's go ahead and put in our equations. So we have MGH equals what? 1/2 MV squared plus KE rotational is 1/2 I omega squared. Okay, so it looks like we have too many things to find the ball's speed. If it just says speed, we're going to mean linear speed, not necessarily rotational speed. Okay, so let's see what we can plug in for other things. We have MGH equals 1/2 MV squared plus 1/2. What is I for a solid ball? Okay, I for a solid ball, I just looked it up on my moment inertia table, is 2/5 mr squared. Now, what again? How can we get rid of omega? Remember, v linear velocity is equal to the radius of something times the angular velocity. And again, like when we just think of our friends as they're rollerblading around, the person on the outside is going to have a much bigger linear velocity because they have a bigger radius, while they all have the same angular velocity as they rotate around. So let's go ahead and use that equation to plug it in. So v over r is going to be omega, that's squared. Okay, so let's start to plug things in and cancel. So 1/2 MV squared, 1/2's right here cancel, so I'm left with 1/5 r squared. I can distribute the squared, so it's going to be v squared over r squared. Cool, cancels. And then we have MGH equals 1/2 MV squared plus 1/5 MV squared. Okay, cool thing is, M is in every single term, so that cancels. And then we essentially have 1/2 v squared plus 1/5 v squared. So let's go ahead and find a common denominator and solve away. So it looks like 10 is going to be a nice one. So this is like 5/10 v squared plus 2/10 v squared, which is, what is that? 7/10 v squared. Cool. We want to solve for velocity, so I'm going to multiply both sides by 10/7 and then take the square root, and we got our answer. So velocity is 10/7 GH, and again, that is all under the square root. Great. So I just want to think of one quick side example. So if something was sliding down, so at the top, let's just say we had like a square object sliding down. Again, no static friction can make it move. Then we could say UG is equal to KE translational. Again, no rolling motion. So if we were to solve this, let's just see what we get real quick. So MGH is 1/2 MV squared. So V would just be square root of 2GH. So I want you to think about, is this more or less than what we've just found? Okay, so 10/7, that's like 1 3/7, which is less than 2. So this number right here is much smaller than it would be if it was just perfect sliding motion. I want you to think about why and then check back into the video. So in this case, since we're dealing with rotational motion, some of the energy goes into getting this thing rotating, and it does not go into just making it move down like linearly. So some of that translational kinetic energy goes to rotational kinetic energy, which means the overall velocity is smaller, but there is still the same total energy overall. Awesome. Thanks for watching.